Is time travel possible? Let's explore the science behind it. From Einstein's theory of relativity to wormholes, we delve into time travel. What if the speed of light isn't just a limit, it's a key? In this journey, we're diving headfirst into one of the most thrilling and perplexing frontiers of modern physics, time travel. From Einstein's breakthroughs to speculative science that borders on science fiction, we'll uncover how our understanding of time, motion and light might hold the secrets to bending reality itself. Join us as we explore the cutting-edge science and mind-bending theories that could one day make time travel a reality. Let's start where the modern concept of time travel was born, Einstein's theory of special relativity. In 1905, Albert Einstein redefined time itself. Before him, time was considered absolute, a constant tick of a universal clock. But Einstein's equations showed that time is relative and it flows at different rates depending on your speed. This groundbreaking idea paved the way for modern physics and our understanding of the universe. Today, scientists continue to explore the implications of Einstein's theories, pushing the boundaries of what we know about time and space. The quest to unlock the secrets of time continues as we delve deeper into the mysteries of the cosmos. Here's the key formula: time dilation. According to special relativity, as an object approaches the speed of light, time for that object slows down relative to a stationary observer. This has been tested and confirmed. Atomic clocks flown in high-speed jets tick more slowly than those on the ground. This effect becomes extreme near the speed of light. At 99.999% the speed of light, time slows so drastically that minutes for the traveler could be decades for someone back on Earth. This is the essence of the twin paradox. If one twin travels at near light speeds and returns, they'll be younger than the twin who stayed behind. Imagine the possibilities if we could harness this phenomenon. The future could be within our grasp, and time travel might not be just a fantasy. That's not science fiction, that's experimental physics. But what about going back in time? General relativity suggests that wormholes could be a bridge between different points in space and time. These theoretical passages might allow for time travel, but they remain purely speculative. The concept remains one of the most fascinating ideas in physics. To tackle that, we need to go beyond special relativity and into Einstein's later work, general relativity. Here, gravity isn't a force, it's the curvature of space-time itself. Massive objects bend the fabric of space and time, and that curvature affects how time flows. The stronger the gravity, the slower time moves. This is called gravitational time dilation, and it was famously visualized in Christopher Nolan's Interstellar, where time near a black hole ticks far slower than time elsewhere. Now, let's explore another fascinating concept: wormholes. Wormholes are theoretical passages through space-time that could create shortcuts for long journeys across the universe. While wormholes are still purely theoretical, they offer exciting possibilities for future space travel and time manipulation. But general relativity offers even more tantalizing possibilities, like closed time-like curves, or CTCs. These are paths through space-time that could, in theory, loop back on themselves, allowing someone to return to an earlier point in time. Theoretical physicist Kurt Gödel, a contemporary of Einstein, found a solution to the equations of general relativity that allows for a rotating universe with CTCs. Later, other physicists found similar solutions involving massive rotating cylinders, known as Tipler cylinders, or certain kinds of wormholes. Albert Einstein, the father of general relativity, was skeptical of time travel. He believed that the laws of physics would prevent such paradoxes. However, Gödel's solution suggested that time travel might be possible within the framework of general relativity. This opened up new avenues for theoretical exploration and debate among physicists. That brings us to wormholes, shortcuts through spacetime. First proposed by Einstein and Nathan Rosen in 1935 as Einstein-Rosen bridges, wormholes could theoretically connect distant regions of the universe or different times. But there's a catch. Wormholes collapse too quickly for anything to pass through unless they're held open by exotic matter, a hypothetical substance with negative energy density. This negative energy isn't just science fiction. The Casimir effect, an observed quantum phenomenon, creates a small negative energy region between two metal plates. Could this be harnessed to stabilize a wormhole? Theoretical physicists are exploring this possibility. If successful, it could revolutionize our understanding of space-time travel. Imagine a future where distances are no longer a barrier. Physicist Kip Thorne explored this idea seriously in the 1980s, even consulting for Interstellar. He found that if one end of a wormhole experiences time more slowly than the other, say by orbiting near a black hole, then you could, in theory, use it for time travel. But of course, theories don't come without paradoxes. Quantum physics introduces a whole new realm of possibilities and challenges. These paradoxes often lead to groundbreaking discoveries and innovations. The interplay between time travel and quantum mechanics is both fascinating and perplexing, pushing the boundaries of our understanding. Time travel to the past invites the dreaded grandfather paradox. If you travel back and prevent your own birth, how could you have existed to make the trip in the first place? To address this, some scientists propose the Novikov self-consistency principle, which states that events in space-time are self-consistent and any actions taken by a time traveler were always part of history. Others explore the many worlds interpretation of quantum mechanics. Maybe going back in time creates a branching timeline, a parallel universe. So you wouldn't change your own past, but create an alternate version of it, existing alongside your own. Let's shift gears and explore the speed of light itself. Why is it the limit? According to relativity, as you approach the speed of light, your mass increases exponentially. To accelerate a particle with mass to the speed of light would require infinite energy. Light is massless, so it travels at this maximum speed naturally. But is there a workaround? Scientists have proposed several theories, including wormholes and quantum entanglement, as potential methods for surpassing the speed of light. These concepts challenge our understanding of space and time, opening new possibilities for time travel and faster-than-light journeys. Enter tachyons, hypothetical particles that always move faster than light. If they exist, they could be the messengers of backward causality. However, they've never been observed and may be more mathematical artifact than reality. There's also the idea of warp drives, like the Alcubierre drive proposed in 1994. It involves contracting space in front of a spacecraft and expanding it behind, effectively moving faster than light without locally breaking the light speed limit. NASA's EagleWorks lab has explored this idea, and physicist Harold White even claimed to find tweaks that could make it require less exotic matter. It's still theoretical, but it's not impossible. Another fascinating concept is wormholes, also known as Einstein-Rosen bridges. These are theoretical passages through space-time that could create shortcuts for long journeys across the universe. The idea is that a wormhole connects two distant points in space, allowing travel between them in a much shorter time than it would take to travel through normal space. While this remains speculative, the potential for wormholes to revolutionize space travel is a tantalizing possibility. Let's not forget quantum physics. In quantum entanglement, information between entangled particles appears to travel instantaneously. While this doesn't allow for faster-than-light messaging, due to no signaling theorems, it does suggest that spacetime and causality might not be as fixed as we once believed. Some physicists are now exploring the idea that space and time are emergent, not fundamental, but derived from deeper informational or entangled structures. In this view, time travel might not require breaking physical laws. It might simply mean navigating a different layer of the universe's architecture. This could revolutionize our understanding of reality. So where does that leave us? Time travel remains unproven, but it's not disproven. The universe, as we understand it, does not forbid travel through time. It only demands that we obey certain strange rules. The mysteries of time continue to intrigue scientists and dreamers alike, pushing the boundaries of our imagination and understanding. Every discovery in physics once seemed impossible. Flying, electricity, quantum teleportation. And now we observe them, we build them. Time travel might be like that too, just waiting for the right questions and the courage to bend what we thought was unbreakable. The future of time travel is not just a dream, it's a frontier waiting to be explored. The journey has just begun. Because time, it turns out, is more flexible than we imagined. And the speed of light? It's not a wall, it's a doorway.